Welcome back, everybody. Today, we're going to be doing a deep dive into something pretty cool, integer sequences, specifically one that's caught our eye, sequence A00000036 from the OEIS.
Oh, yeah. A00000036. That's a fun one.
Yeah, and for our listeners who might not be familiar, the OEIS stands for the Online Encyclopedia of Integer Sequences. It's basically this massive online database.
It's amazing, really.
It is. Instead of books, though, it's like a giant library of these fascinating sequences of numbers, each one with, its own unique story to tell.
It's really a treasure trove for anyone who's curious about patterns and numbers, really.
Exactly. What's particularly interesting about A000036 is that it connects to this classic problem in geometry.
Ah, yes. Counted the points.
You got it. Counting how many points on a grid, like graph paper.
A lattice.
Yes, a lattice. Fall inside a circle.
You'd think it would be pretty simple.
You really would.
But trust me, it gets way more complicated than you might think.
Way more complicated. So can you walk us through this? What exactly is A000036 describing? Like, what's the story here?
Okay, so picture a grid, like you said, graph paper, where each crossing point represents a pair of whole numbers.
Our integers?
Exactly, our integers. And that's what we call our lattice. Now imagine a circle right smack dab in the middle of that grid, centered right at the origin.
Okay, got it. I'm picturing it.
So as this circle starts to expand, A000036 tells you exactly how many of those lattice points, those points on the grid, end up inside that circle.
So we're basically counting. It's like those points are getting swallowed up by the circle as it grows.
Right. Exactly. It's like watching those grid points get absorbed by the circle's expanding boundary.
Very cool. And there's a formula for this, right? For this point counting adventure.
Oh, there absolutely is.
Lay it on us.
We call it A of n. It was pretty straightforward. N is simply the square of our circle's radius. Plug that into A of n, and boom, you get the precise number of lattice points nestled inside.
Okay, so far so good. It seems pretty simple. But you mentioned earlier things get tricky, right? So where does the complication come in?
Well, intuitively, you might think that the number of points we count inside that circle would be pretty darn close to the circle's area, right?
Yeah, it seems logical. More space, more points.
Right. But that's where things take this really interesting turn. They don't quite line up as neatly as you'd think. We can calculate the circle's area, which we'll call V of n, using good old pi times n, our radius squared.
Pi times n, classic geometry.
But here's the thing. When we compare that nice, clean area calculation to the actual point count from A of n, well, there's often a difference, sometimes even a big one.
A discrepancy between our neat formula and the messy reality of counting points.
Exactly. And we call that difference, that gap between expectation and reality, P of n.
Yeah.
Like our measure, how much our intuition about area and point counts just breaks down.
Hold on, let me make sure I got this straight. So we're talking about the difference between the actual countable points on that grid and what we'd expect based on the circle's perfect smooth area. And that's what makes A000036 so special.
You got it. It's all about exploring that gap between the neat and tidy world of integers and the smooth, continuous world of geometry. And to make things even more interesting, A000036 doesn't just list any of these P of n differences. It's picky. It focuses specifically on the closest integer to P of n.
Okay, so it rounds things off a bit, makes it a little tidier.
In a way, yes. But here's the catch. It only does this for very specific values of n, values that come from another sequence entirely. A00000009.
Whoa, wait a minute. A sequence within a sequence. What is it about A00000099 that makes it so special? Why is it calling the shots for A00000036?
So think of A00000036.
We'll think of A00000099 as a drama detector.
Drama detector. Love it.
It swoops in and lists the values of n where this P of n. Remember, that's our mismatch between actual points and the expected area where that hits a brand new record, a new extreme. So a 000009 is pointing out the moments when our intuition about point counts and area goes totally haywire.
Exactly. It's highlighting those cases where the mismatch is the most dramatic, the most unexpected.
Okay. Wow, my brain is definitely starting to see why this isn't your everyday count the dots problem. So just to make sure I'm following, A00000009 picks out the most extreme cases of this point area mismatch, and then A000036 comes in and gives us a rounded look at the difference in those specific dramatic cases.
That's precisely. And to really appreciate just how wild things can get, let's look at the first few numbers in A00000036. Ready?
Hit me.
7, 2, 3, 5, 6, -6, 7, 8, 10, 13.
Okay, whoa. There's no way I could have predicted that. It jumps all over the place, positive and negative. It doesn't seem to follow any kind of obvious pattern. That's not what I'd expect from just counting points in a circle.
Right. There's clearly something deeper going on here. And, if you really want to delve into the nitty-gritty of how this all works, there's a formula section in the OEIS entry for A000036.
Of course there's a formula.
Oh, yes. It shows exactly how it's all derived from our P of n, that difference in those special n values from A000009 to 9. But the thing is, even with the formula, those unpredictable jumps and dips in the sequence, they're still there. They don't just disappear.
It's like the formula captures the chaos, but it doesn't quite explain it, right?
Exactly. And, another thing I noticed is that A000036's entry also has an extension section.
Oh, that's interesting. What's that all about?
Well, it shows how the OEIS is this, living project that's constantly evolving and growing. Basically, what it means is that multiple people have contributed to A000036 over time. They've refined it. They've added new insights. It's a really cool example of how math isn't just about, those lone geniuses working in isolation.
It's a collaborative effort.
Absolutely.
Yeah.
It really is a community effort to kind of unlock the secrets of these fascinating sequences. It's pretty inspiring when you think about it.
I love that. Okay, so we've got this seemingly simple question about counting points in a circle, but it's led us to this, well, frankly, amazingly intricate and unpredictable sequence, 80000036. So what's the big takeaway? Why should anyone really care about this? What makes this important beyond just the math itself?
That's the real heart of it, isn't it? What we're uncovering here, it goes way beyond just one sequence. As fascinating as it is, it touches on these fundamental ideas about math, about how we approach understanding the world around us, really.
Ooh, okay, I'm intrigued. Tell me more.
It really does. What we're seeing here is this really fascinating clash between two big ideas in math, continuous stuff and discrete stuff.
Okay, I'm following, but break that down for me. What exactly do you mean by continuous versus discrete? Give us the Math 101 version.
All right, so think of geometry, with all its smooth curves and lines.
Circles.
Exactly, circles. That represents the continuous side.
Yeah.
You can take a line and keep dividing it into smaller and smaller pieces forever, theoretically at least.
Infinitely small. Okay, got it.
But then we have number theory, the world of whole numbers, integers. That's all about the discrete. You can't have half a point on our grid.
Right.
Nope. It's either there or it's not. So what you're saying is that our circle problem is trying to take these neat, tidy, whole numbers, these integers, and fit them into this smooth, continuous space of the circle.
Exactly. It's like trying to build a perfect circle using nothing but square blocks.
I like that analogy.
No matter how you arrange those blocks, you'll never get a perfectly smooth curve. There will always be little gaps, little overlaps.
And those gaps and overlaps, that's what our friend P of n is capturing, right?
Yeah.
That difference between the circle's nice, clean area and the actual point count.
You've got it.
Yeah.
And the fact that P of n can get so large, especially for those special values highlighted by A00000099, well, it tells us that this tension between the continuous and the discrete, it's not just some minor detail. It has real consequences.
So it's not just a theoretical curiosity. It's something that actually affects how we do math and interpret results. Absolutely. And this brings us to another crucial point, the nature of approximation. We use continuous models all the time, like calculating that circle's area, to represent things in the real world.
Makes sense.
But we have to remember, those models are just that. Approximations.
Right. They're representations, but not always perfect reflections of what's actually going on.
Exactly. And a 00000000 fix is like this flashing warning sign, reminding us that sometimes those neat and tidy models we love so much, well, they don't perfectly match the messy reality of discrete data.
It's like a reality check for mathematicians. Like, hey, don't forget, your models aren't always perfect.
Exactly. Don't get too attached to those perfect circles. So are there any real-world situations where this knowledge about the limits of approximation really matters?
Yeah, that's a great question. It all sounds very theoretical, but does it actually have any practical implications?
Well, let me give you an example. Cryptography.
Ooh, cryptography. The world of codes and ciphers. Okay, you've got my attention. How does counting points in a circle relate to keeping our secrets safe?
A lot of encryption schemes are built on using really tough mathematical problems. The harder a problem is to solve, the more secure your code is. So imagine trying to crack a code that's based on a sequence like A00000036 with all its crazy jumps and dips.
Yeah, good luck with that. That sounds like a computational nightmare.
Right. So this seemingly abstract math problem, counting points in a circle, could actually help us protect our data online, keep our communication secure.
So this isn't just about some theoretical tension between continuous and discrete. It's about real-world security. That's pretty mind-blowing.
It really highlights how even the most theoretical areas of math can end up having these very real and practical applications.
Okay, so far we've talked about this tension between continuous and discrete math. We've seen how it plays out in A000006, and we've even touched on potential applications in cryptography. But I still feel like there's more to uncover, like we're just scratching the surface of the sequence's mysteries.
I think you're right. One of the most exciting things about sequences like A000036 is that they often hold these hidden patterns and relationships, things that aren't immediately obvious.
It's like they're hiding secret codes within themselves. So even though it might look random at first glance, there could be all sorts of deeper structures lurking beneath the surface, just waiting to be discovered.
Exactly. Mathematicians have developed all kinds of sophisticated tools and techniques to analyze these sequences. They're looking for subtle regularities, recurring motifs, unexpected connections to other parts of math.
It's like those magic eye pictures. You have to stare just right to see the hidden image. So what you're saying is there's more to A000036 than meets the eye.
Absolutely. And the search for those hidden patterns, that's what keeps mathematicians coming back to these sequences again and again. We talked earlier about how A00000036 is built on top of another sequence, A00000099, the one that highlights those dramatic moments where the mismatch between the circle's area and the point count hits a new record.
Our drama detector, as you so aptly put it.
Exactly. It's like A000099 is the spotlight, shining brightly on those points where the tension between the continuous and the discrete reaches its peak. It's like the director yelling, "Action!" at the climax of a scene.
And it's not just a passive observer. A000009 is an active participant in this whole point counting drama. It's selecting the scene, setting the stage for A00000036. What's even more interesting is that A00000099 itself is full of mysteries, right? It's not just some simple list of numbers.
Absolutely. It's a sequence with its own set of puzzles and unanswered questions. Mathematicians are still trying to figure out how those values in A000009 are distributed. Like, are there any underlying rules governing their growth, their behavior? It's a mystery within a mystery.
Wow. Okay. My mind is officially blown. So we have this already incredible sequence, A000036, built on top of another sequence, A00000099, which is also full of unsolved riddles. It's enough to make you dizzy. But I think what's really important to remember is that this isn't just about numbers and sequences, right? We're grappling with these bigger concepts like continuous versus discrete, approximation versus reality, the interconnectedness of different branches of math. It's a lot to wrap your head around.
You're hitting on something really important here. Exploring A000036, it's not just a mathematical exercise. It's a journey through these fundamental concepts that underpin so much of our understanding of math and the world.
And as much as I'd love to keep going down this rabbit hole, we are running out of time for a deep dive today. So for our listeners who are now hopefully as fascinated by A000036 as we are, what's the one big takeaway you want to leave them with? What should they ponder as they continue their own exploration of the sequence and the wider world of the OEIS?
I think the biggest thing to take away from all this is to never underestimate the power of a simple question. Sometimes the most amazing discoveries come from asking those seemingly obvious questions, the ones that maybe nobody else thought to ask.
It's like that saying, the most profound questions are often hidden in plain sight. And it seems like the OEIS, with its, well, frankly, its overwhelming collection of integer sequences, is like the perfect place to go hunting for those hidden gems, those questions that lead to breakthroughs.
It really is. Each sequence in the OEIS, no matter how simple or how complex it might seem at first glance, has this potential, to unlock a whole world of new mathematical insights. It's a playground for curiosity.
So for our listeners who are ready to dive into the OEIS themselves, where do you suggest they start? What advice would you give?
Well, you can start with the sequences we've talked about today, of course. O00000036, its partner in crime, A00000009, and even those mentioned in the cross-ref section. That'll give you a taste of the incredible variety and depth that the OEIS has to offer.
And don't be intimidated. I know it can look a little scary with all the math jargon and the formulas, but remember, a lot of these ideas, Even the really complicated ones often have pretty simple explanations at their core. It's all about finding those explanations.
Exactly. Just approach the OEIS with a sense of, I don't know, a sense of playfulness. Don't be afraid to experiment. Try things out, look for patterns, ask your own questions. You never know what you might discover.
It's like going on a treasure hunt, a mathematical adventure, with the OEIS as your guide, and who knows, maybe one of our listeners will be the one to discover a new connection, a new pattern that changes how we understand all of this.
That's the beauty of math.
Hmm.
There's always more to learn, more to discover. So yeah, dive into the OEIS, embrace the challenge, and let your curiosity be your guide.
That is a fantastic note to end on. So, to all our listeners out there, thanks for joining us for this deep dive into the fascinating world of integer sequences. We hope you've come away with a newfound appreciation for the beauty, the complexity, and the endless possibilities of math. Until next time, keep exploring, keep questioning, and keep diving deep.